Good morning. I'm Stritzinger, and my main application for Erlang is using it in embedded systems and for industrial and automotive customers. And today I'm talking about one application that we are about to do, or we are almost done. It's about PLCs. Who knows what a PLC is? Okay, that's not too many. PLC is a Programmable Logic Controller. These are used in industry for basically everything. Everything that moves or switches or goes on and off and controls motors, like the thing when you go into a parking garage that opens the gate, and all this stuff is done with PLCs. These come in different sizes, and they are basically the workhorse for everything. And they are programmable. Who knows how a PLC is programmed? Oh, even someone, yeah. There's a complete whole separate world how PLCs are programmed. There are some standards. It's like they only have numbers. The normal standard is IEC 61131, and actually the largest company who is selling PLCs in Europe has their own standards. They are not doing this, but the rest of the world is using the standards. And inside the standards are all kinds of ways to program them, several ways actually. The first one is a quite old one. And there's also a new standard for distributed PLCs. So you might notice how this might be connected to Erlang, distributed PLCs. Maybe we could contribute something because we know how distribution works, or at least we believe. So how do we program these? The start of PLCs, the first thing that the first PLC was invented. I think it was at Ford. I don't know. I'm not very sure. But it was invented to replace like hardwired relays, who switch on and off stuff and control each other, have time delays and all these kinds. Because every time they needed to change the process for the manufacturing, they needed to rewire, bring in the electrician and rewire all the relays. So the first kind of way to program these is derived from the relays, and it's this part. Oops. It's this way. This is basically the plan how the electrician would wire the relays, and these were encoded in a programming language. And I actually copied this out of the standard. It's even like with all these dashes and like with this ASCII arts. So what does this mean? We have a wire like running from here to here, and we can have multiple wires. So a big PLC program has thousands of wires. And at the end of the wire, there's a coil. There's this one. That's a coil. Coil means a relay, the coil of a relay. I mean, relay has two parts, the coil, where you trigger it, and the actual switches. So the coil, if it gets current, it switches something. And so this is related, this run here is related to this run. So if this coil gets current, it closes this switch. That's a switch. So what we have here is basically a industrial start-stop. That's the easiest connection to like start a motor, where we have a key that starts the motor, but the switch is not always on. It's like only a push button. And so if somebody, and the switch is this one, the start, if somebody pushes the switch, and the emergency stop or the emergency switch is not switched off, the slash is an inverted switch, then the coil gets energized and switches on this one, which makes the whole thing holding because it keeps energized, unless the stop switch is being pushed. So this is actually totally concurrent. I mean, if I build it with relays, it's concurrent. I mean, it's like everything is happening at the same time. And you can have like multiple lines like these controlling each other. So when they brought it into a controller, they need to like change the way it was running because yeah, well, it's not running everything at the same time. So and what they did is like they run the program cyclically. Everything in a PLC, in a classical PLC, runs in a cycle. So the program is run every, like, let's say 20 milliseconds. And the size of the program and the size of the PLC depends, gives you basically the real-time guarantee, like the cycle time. If for more complicated stuff, then can be switched with relays. There's a assembler-like programming language called instruction list. This is the past, so we move on. Okay. Let's move to the normal thing. Did I skip one? No. So, but they're still in the standard and they are still used. Especially the relay plan is liked by electricians. It's how they program. There's a different language from the assembler language, which is a little bit Pascal-like. You can see it below here. So it has, you have to declare variables, they have data types, you have function calls like this. And you also have functions with multiple inputs and outputs. So multiple return was a thing back then already, and then you have to like keyword things. So the input in one is getting the output of the cosinus, and the input in two is getting the output of the sinus, and this is actually the output lines. The enable out gets the enable in, and you can also draw this, and this is also like standardized in this ASCII art, but usually modern tools don't use this anymore. You can use it. It's allowed to use real graphics, and this is basically the diagram you see here is encoding the same program than we see here in the Pascal-like language, which is called structured text, by the way. And the other thing is function block diagrams. I need to say something else. With the function block diagrams, what we have here, these function blocks, they don't have any state inside them. They're stateless. They're actually functional. They are standardized not to have side effects. That's it. So usually you want some side effects, so there's something different that's called a function block. A function block is basically similar to a function here. There's inputs and outputs, and it has a state. It has internal variables that are kept between runs, basically like the static variables in a C program. So if it's run cyclically, it keeps this internal state, and then you can have you can build all kinds of side effects because the internal state might be connected to some outputs. And in the classical PLC programming, there are lots of global variables also. Everything is global. So that's not so nice for us to implement. Fortunately, we have something different. And there's also several ways of a higher level of programming these. This is a sequence function chart, also standardized. We are still in the first standard, in the IEC 61131. What you see here is basically a state machine. Actually, it's a Patronet, because you can, oops, that's too early. What you have here is basically you have states like this. These blocks are states, and there are transitions here. These bars here are transitions, and they're connected. And it's basically, the state machine is like a starting state here, and if this transition gets true, and you can have like either a condition, or you can have the output of a relay plan. If the condition gets true, it moves on. This state is no longer active, and this state gets active. And basically, the cyclic program is running inside the state. So if this is active, this one is running in cycles. And if this gets active, this gets stopped, and this runs in cycles. And what the boxes on the side, they're actual actions. So there is a simplified way to specify the actions. And they have flags like, this is a delayed action, this is a... So to ease the normal use cases of the programmers. And you can have complicated plans, and you can have also like something like this. This is a condition. So if either this or this is true, it moves either there or there. So it's a either or. And if it's a double line, it's a parallel. So if this triggers, which it always does because it's start state, this runs and this runs in parallel, or at least concurrently. And you can also have a join when both end states are active. You can join them together, etc., etc. But yeah, we're not actually using these. I think I need to talk about the application area where we want to use this, because what we are doing is, what my customer is doing, is building these. It's a company called Bosch Rexroth, German company, subsidiary of Bosch, and they are building transport systems. So everything that moves the material flow inside manufacturing. So you have all kinds of sizes. The left one is a medium size. Up there you have for large solar panels, special wide ones. And there is also, this is like a chain belt for small pieces. And so all kinds of movement for the manufacturing. And this movement has all kinds of, if you want to go left or right and stuff like this, and then you move the stuff. You need the thing over there that's actually a belt that's always moving. And if you want to move it to another belt, it gets lifted off and moved to the other belt, and you need to control this stuff. And initially, what I did for the customer is I helped them build these, which is basically an RFID system, which was not called RFID back then, with a proprietary tag, which has actually is nicer than the standard tags we have now, but the standard tags are much cheaper, so we are doing the standard tags now. The little white box is the actual tag. It's a real box. And so the pallet where the product is on it has information in it. It gets tagged. And what they had back then was a distributed production system where the whole product plan is on the tag. So the product knows what needs to be done next. And this is very robust because it's just decentralized. You have no central server that breaks and you stop production. And so I like this very much. I like decentral stuff. So this was just a kind of smart RFID system. It had a cache. It was written in C. Back then I used the operating system RTEMS, which is an open source hard real-time operating system, which we'll hear a little bit more about later. And so we started out building RFID systems. So our next system will be also a RFID system, but it will be more smart. It will be written in Erlang. Actually, it is already written in Erlang. But there will be layers for like intelligent material flow, like doing some online planning, like changing plans if a machine breaks, rerouting stuff, and also features to try to avoid reading the whole tag all the time, because if you want to read the whole tag, it takes so long that you need to stop the product for reading the tag. So if you can read a few bytes while it drives through quickly, and so if I want the rest of the data, I need to stop it actually, and that time is money in production, and so we want to avoid this. So what I'm doing is basically I cache the RFID data in the node, and I send it along in the network, having basically a kind of distributed database of RFID contents. So if it already knows the content, it doesn't need to stop it. It can just go through. But the main thing is the online planning stuff. So, but what we also want to do is like we want to avoid having a PLC at every node that moves all the parts, because yeah, if you only need one part, it's cheaper, and that's a selling point. So we want to have a software PLC inside our node, and that's a usual approach. You can buy like ready-made firmwares for software PLCs, but those are written in C. Those have problems with concurrency and all kinds of stuff, and they don't integrate very well with our Erlang code. So we decided that we do our own software PLC. And, well, so we need a compiler for these languages. So I wrote one in Erlang. And that's about the core of the talk, and the demo is showing this. So here's the slide. It's like in a research project. There's some money from the German government flowing into it. So the system has good funding, and what we want to achieve is that the PLC, because normally I could write all the control processes for moving the parts in Erlang, of course. That would be actually much neater. But I don't want to do it. I want to use the hundreds of PLC programmers that are at the customers, because they have people who know this. And they actually know the machines better than me, much better. They know how to get stuff moving and how it works. And we want to give them a way to program our node to get the moving parts. And all the artificial intelligence, super smart part, we do ourselves. So with all these global variables and running in cycles, that doesn't sound too nice to be implemented in Erlang. And I was like thinking a lot how I can avoid running in cycles and turn global variables into messages. And then, fortunately, I found out about that there's a new standard, the second one I showed in the beginning, for the distributed PLCs. And since they needed to standardize the distributed PLCs, they needed a solution around this running in circles, because if you're distributed and networked, you can't like send all the time. I mean, there are solutions to this on field buses, but that has no future, basically. So what they added to the function blocks that has a state inside is events. And I liked it very much, because it very neatly maps to Erlang processes. So what we have here is the way a function block is drawn. It has like this little head in the top, and the lines that go into the top and come out of the top. So inputs are left and outputs are right by convention, and the lines going into the head are actually events. So it's an event which basically is not a... They emulated it. Maybe you remember the enable in, enable out of the function blocks before. So they had an enable function block for error handling, mainly. So you can switch off the function block. So it does just an if around the cycle and just jumps over. But they replaced this, and the events are actually instantaneously and not at the same time being present. And in the body of the thing, you have the actual data, inputs and outputs, and these inputs and outputs can be connected to events. So this line here, that's actually the connection to event. So the event vote is combined with this data, which means the data is only valid if the event triggers. Otherwise, you can latch the data, but you can't read it from the lines if you have something. And the output event, it's the same. So this means that this data is only valid when this event triggers on the outgoing side. So that's actually pretty neat for mapping to Erlang processes, because what I did is mapping events plus data to messages. I want to show you a little bit of code. Are we in the time? Okay. So this is actually structured text code, how this function block, it's a voter, which is basically doing the following. If the reset event comes, it gets reset and the output gets to 0. And otherwise, if the vote event comes, it does a voting between the input lines. And if 2 or more are actually true, then the output is set to true and latched. It's kept true until it is reset. Those PLC programmers use stuff like this. They were immediately nodding when I was showing this. Yeah, you need something like this. Okay, I don't know exactly what they're doing with it. So what we have here is we have the function block. It has a name. It's voter. We declare the event inputs, and in the declaration, we already have this with statement where we connect the event to the data. So this means the event vote is connected to the data inputs A, B, and C. So we can specify what we have in the drawing. We can specify also in the programming language, one-to-one. And then we have the input variables, and we have the output variable. And you see the output variable voted is also connected to this output variable here. So that's the declarations. Let's look at the actual code. What they did is they actually included a state machine, because usually they build state machines out of the elements. So it's very similar to the sequential function chart I showed before. So they need a state machine inside, and they're actually providing it. It's basically a gen FSM. So what you do is you declare the states in the beginning. So there's a ready state and a voted state. It's a very simple block, not many states. And connected to a state is an algorithm. In this case, the reset algorithm and the vote algorithm. So that's some code that can be run. And an output event. Ready is an output event, and voted is an output event. So when this state is triggered, the code is run, and then the event is sent. And you can actually have multiple pairs of codes. Like this can be a list of algorithms and output events that will be run once it's triggered. And so how is it triggered? You have a transition diagram specified in the transitions. Basically, you say ready to voted, and then you say this happens when the event vote happens. And you can also have conditions. You can have, say, ready to voted, vote when, actually it's the same keyword, I don't have it in example, vote when variable A has this value, and etc., etc. So they basically have actually guards on these transitions. And here we have the algorithms which are run when the event triggers. The reset algorithm just sets the state to 0, and the vote algorithm, if the state is 0, then it calculates the actual voting and sets the state, and that's it. That's the whole context of this voter thing when programmed. So what we want to do now is we want to translate this into Erlang, or actually into a Beam file, which we can then run in our Erlang embedded system. So that's what the compiler is about. Compiler is looking like this. Simplified, of course. There's the compiler driver, the thing on the top left, and which reads the actual code, the ST code, standard text, and runs through a scanner, through the parser. The scanner is done in LEX. It's basically the Lex variant of. For those who don't know, does everybody know Lex with double E and YEC with E? Yeah, is it known? It's basically the Lex and YEC implementation in Erlang, which comes with OTP. So it's very convenient. You just have the tools for building a compiler. So you have I just could apply what I know about writing compilers, like very easily. And then there's one module which is a little bit, which has actually multiple passes. It's like massaging of the abstract syntax tree a little bit. What I implemented is like a microparse approach. So I have lots of tiny parses which I can like assemble, which is quite neat. And the module ST Core is then actually producing Core Erlang. Core Erlang is an intermediate language in the Erlang compiler that's actually specified. So it's a very, very simplified Erlang, basically, which has easier scoped variables. They have basically let. The let we don't have in Erlang, we have in Core Erlang. And this is actually neat because what we don't have in structured text, we have mutable variables. We don't have immutable data. So we need to emulate this somehow. And I did it like, I just basically nested the scopes of the variables. So if it gets a new value, I just make an inner scope, because then I can set it again, and it has a new value. You need to take a little bit care if you want to like translate an if, because maybe you set the variable before the if, and then you overwrite it in one branch and overwrite another variable in the other branch. And at the end, everything, the code that runs at the end, needs to get all these changes. And basically what I do is I map it to a case, and I track which variables is alive where, and I return all variables that is modified in any branch of the case. And I get this back as functional result, and I can set my new let variables for the next scope. So besides of having to track the variables, but I mean, you need to track some variables if you're writing a compiler. So couldn't get around this. And after I produced the core, I just call compile from core. There's the normal Erlang compiler module has the normal compile function where you can pass in several forms. And if I specify the option from core, then it basically produces a beam file from the core. This beam file then needs to run. So we need a runtime system. So we have the runtime system. We have the actual runtime system for the function block. We map every function block to a process. So every process runs this fb run code. So there's lots of fb run processes. And the voter beam file is actually a callback module. There are only callbacks in it. And it calls into this voter beam to find out about the variables and stuff like this. And the voter beam also calls like a library module for runtime library for standard functions and everything. So this in a little bit more detail. Here we show how these function blocks communicate actually. I'm actually a little behind. I have to speed up a little bit, but that's actually important detail. So I tell you this: you have the actual runner thing. That's basically like a gen server. That's a special process that can get supervised, and it calls into the voter. And if it happens that it wants to send an event, it needs to produce a message, and needs to find out where it sends the events, because there's this graph where the stuff is wired, and these function blocks. There's another specification language, or several again, XML and non-XML and all kinds of things, or you have a graphical tool. And from the wiring, I produce a function that's called FB targets that tells me which event from which instance, because that's actually the voter function block has an instance name, vote1, which is globally registered. And it gets these information and finds the target out1 where it needs to send the message to, in the formatting of the output event. So it sends the message, basically it puts in the sender information, like which function block, which name, it has the event, and it has the data that's connected to the event, to the on the output side. But then I need to map it back, because the output data is mapped to some input variables. And this is done basically here. I have a block basically, a helper function that maps these, that gets the function block and the message content, and the state of this process, which is basically all the variables. And it knows from, it's generated at the same time like the blue one. The blue ones are generated, and gives me my new variables, my new state, and also my input event name, which I need to trigger. And then I can actually trigger the actions and stuff moves on. So let's move on. There's a few tips for Core Erlang. You can look it up in the slides. The function I'm using the CERL module, which is basically syntax tools for Core Erlang. You can also build the AST manually, but I was recommended this, and I went this way. It's basically a matter of taste. There's one function, it's called CERL abstract, which is actually not badly named because it actually makes a literal. So you have any Erlang term, and if you shove it into abstract, it makes a literal Core Erlang thing. There is also the name literal, but that doesn't do this. Abstract does it. And the important calls is, if you're developing, add to your options this one, which calls the Core Erlang lint, which is not normally called. because it's like not trusted really. But for debugging your own problem, when you start generating Core Erlang, it's very important. Also report errors. And the next thing is copy the file core.lint from the compiler and uncomment everything, every output that's in it, and run with this, because then you actually get more meaningful places where you, because in the beginning you will screw up building the right core syntax tree, and you need to find where it is, and it actually prints the actual statement that it can't digest, because otherwise you get very bad error messages. So normally we have, that's a normal flow. Event flows to the same block with the data. So the event line goes into the same block and is connected, everything easy. So that's the easy way. But somehow they also specify this way. So the data goes from this block to that block, but the event goes through another block or a bunch of blocks. Well, that's actually bad for mapping to messages, because if I map this to messages, then I need to make sure that this data arrives before this event, and just before, not some other data message arrives in between and stuff. I need to synchronize it somehow, and I don't want to synchronize it actually, and because even while this goes through another block, you know, it can come in out of order, because that's another process. And what I do at the moment, I was thinking about use some logical clock thingy, but then it got not. It didn't lead to anything, and then it occurred to me that I just mend the data flow graph before I compile it, because it's actually very easy, because there are in-out variables that just go through, and I just move the data along with the event and add virtual in-out variables to the blocks where it moves through. And after I did this, then I move a lot of data around that's not needed, but in the next pass you can actually remove everything that's not needed. And so that's actually pretty lean, and I don't need any synchronization stuff. I just send the message. So there would be a demo here, but I'm short on time, so I think I make one. I plan 2 demos. I make 1 demo. I have one big demo at the end. I also skipped through the slides because I've talked about this before. I ported Erlang to the RTEMS hard real-time operating system, and yeah, that's the features of the operating system. You can read it yourself. Initially, I built this thing. That's a product of mine. It's a flashing system for the automotive industry. But in this system, Erlang runs on FreeBSD and talks via USB to the gateways running on RTEMS. For the stuff we are doing in this product, we needed something more integrated, running on small boards. That's the new project name, GRISP, running Erlang on RTEMS hardware and having support libraries and stuff like this. There's a website, but it's very inactive. But when something will be when something will be shipped, like about in 2 months, it will appear there, the patches. That's how the system looks. You have the Erlang code, goes through the Erlang runtime, which uses the normal drivers to talk to the POSIX layer in the actual RTEMS system, where you have networking and file system, for example, goes through the network. You have also a C application who talks to the RTEMS and the hardware. But you can have NIFs and LinkedIn drivers that actually talk directly to the hardware, because that's the way you do it in the small embedded systems. You don't have a driver layer. You write your driver. And what I can do now is I write the driver right as an Erlang LinkedIn driver. And that has very low latency from Erlang to the hardware, the lowest you can get. So now it's time for a demo. So what I have here, you can look at it. There's no time to show it with the camera. I have here a small board, which is connected to my laptop by network. And actually, we have multiple boards that are networked, and Erlang distribution works. And there's an output relay board, because I'm driving this, and lamps are basically a short circuit when they go on, and only get their nominal current when they're on, and the power switch is off so fast of the current control of the output driver, because actually they could drive it directly, but I need to put in relays. And I also have some sound system, but yeah, you won't hear too much. So let me switch it on. While I talk, is it on already? No. Normally it boots in 3 seconds from, I've showed this, I've demoed this in other conferences. But somehow I was like a little bit in a hurry while preparing this, and it was, I think there's some distributed application stuff left over that waits for the other node that's not there. So it takes 30 seconds now until this times out, until it boots through. So this is not normal. Normally it's immediately on. 3 seconds from power on to Erlang shell. Basically, let me close this. We don't need this at the moment. Yeah, I shortened this. Actually, I wanted to show you like the core Erlang code I actually produce and run the compiler and stuff like this. I just go to the last demo. Not enough time. Ah, it woke up. So it's a blinking light. And so we need demo 2. We have demo 2. That's I start distributed Erlang, and I do a net admin ping, which I put into my user defaults, and I get the pong. So I'm connected to the actual to this system. We can also have a remote shell in, which is very convenient for an embedded system. So, but we are not actually using this. That's just for testing the distribution. That's the console. I don't need this. I need to like fast forward to. That's actually a remote shell I don't use. That would be the remote shell. Yeah. So I'm running this on the other side, and let's do away with this. Let's actually use this. And the editor. So what runs here is basically 3 function blocks. One block is implemented in Erlang. You can also implement it in Erlang, which is this one, because you have no timing in these events, so you need to produce the first events that have timing. So like something like an event delay or a cyclical event producer that is actually in the runtime system and be used as building block. So what I extended the syntax a little bit by saying that I implemented in Erlang, so I can specify all the variables, but it's implemented in the runtime lib. So that produces the events, and the events go to the events go to this very little. Oh, I'm actually in the wrong directory. I need to skip over to the other directory. So this is the function block we actually run. Let's go to the beginning. We have one event input, that's toggle event, and it's connected with all outputs, with state 1 to state 5 output, and we have the output variables, and we have a very simple state diagram that goes from low to high on event and goes from high to low on event, and it sends actually a toggle event, but we don't use this. And then the algorithm set low or set high is run. And you see, I set the state here. Here I set the state of all the lamps to 0, and here I set the state of all the lamps to 1. It's 4 lamps, all 4 blink. So let's change this. So I put in this state a few 1s, and I need to make care I'm not like switching nothing anymore. And like 1. No, that's wrong. That's actually exactly wrong. I need to do it like this, like the other way around. Okay. So I changed this, then I compile it. I don't have a command line thing for compiling it. No options needed. So actually the binary you see is the actual beam, but it also writes it on a beam file, and I have a small function that does a remote load of the beam file onto the node while it's running. So I do a net load So something needs to change now. Yeah, we changed it. So we changed the bit pattern. That's okay. So let's do another demo because we didn't do everything. Let's change this to 0. I have to say the fifth. Oh, I'm not on the control key anything anymore. So the honking thing that actually is like half of the time it makes the system crash because it pulls too much current when it goes on. So it will probably just go on. It should actually honk on and off, but half of the time it doesn't work. So let me compile this again and load it and hope it works. Would be cool if it would work continuously. Nah. Oh yeah, it works. Yeah, so that's, I relieve you of the sound. So let's move back to the slides. Hello? Yes. Because I want to add some future things. Currently, we run this the function blocks in Beam code, so we don't have hard real-time. We just have Erlang soft real-time, which is hardened a bit by running it on a hard real-time operating system where I can actually control how much the Erlang process is preempted. I can actually avoid preempting Erlang or task switching to another task by the operating system, but it's still soft real-time. Garbage collections happen and all this stuff. But it's actually pretty neat. It's for the use case we are doing it, that would be enough. But wouldn't it be neat if we could have hard real-time Erlang processes? I would find it neat because I could code in I could just reuse this. I don't have to like compile it to C or compile it to assembler and to get hard real-time. I can just get my hard real-time things. So I made a plan, and that's a plan for the future, like for in 2 years. And the idea is basically, how do we get rid of garbage collection? I mean, we need an extra scheduler that runs on a higher operating system priority and can preempt the other schedulers, and we need to make some choices that that limit what we can do in these processes. So my plan is to allow everything in Erlang, but if you use everything and send in huge data, you lose your real-time behavior. So you need to take care. But the same you need to do in C. Yeah, is it hard end or? 1 minute, okay, very quick. So the method is like this. At T0, I get a message. That's the timeline. Then I have the green part where I do the actual processing, which is actually the hard real-time deadline, which is the second time. And I send off some messages to another thing that's hard real-time, for example, network these. And then I have the blue time. That's the recovery time until when I'm ready to get the next message, which basically specifies the message rate. And that's a usual thing to do in hard real-time systems, to limit the message rate for a message passing hard real-time system. So if you look at this, next picture, if you look at this on this slide, so we have 2 processes, and it's earliest deadline first scheduling. So whoever has the earliest deadline is being scheduled, gets the highest priority. So at first we have the highest priority because we have the first deadline. But when we are done, our recovery has this deadline, which is later than the deadline of this process, which already got a message and is runnable. So this has got to run first, and then we have a shorter time to recover where we do our garbage collection. And yeah, I think you get the gist. We have fixed 2-part heaps, so we don't allocate heaps anymore. You have to say how much memory you want to have in a heap, and we allocate 2 of them and copy over. We use the normal garbage collector and copy over the data from one heap to the other. If you run out of memory, you crash. Basically, you can specify what happens, like total crash, restart to the beginning. We can restart to the beginning very quickly. That might be a feature. If you miss the deadline, you crash. If you get too many messages, we limit the message queue size, the input size to 1. If it fills up, if the message is not taken out before the next one comes, then we can configure the sender crashes, the receiver crashes, nobody crashes, the message is dropped, new dropped, alt dropped. You can configure everything, and then we see what we can build out of it. So I'm done. Questions?
Time for a couple of questions. If you'd like to raise your hand, bring the microphone over to you.
There's perhaps a conflict in building PLCs. So on the one hand, the industry wants very, very reliable bits of kit that will run with vibration and diesel fumes and not crash and not have industrial processes sort of blow up or cars run into walls. But on the other hand, they use sort of fairly primitive languages, and you've got a bunch of unproductive programmers who are very depressed and not very agile. So how do you reconcile that conflict? I mean, you're obviously building systems with more parts which can go wrong. You've got schedulers, you've got garbage collectors, you've got operating systems and compilers. How do you sell this into industry and give them guarantees that that things aren't going to blow up unnecessarily?
Yeah, that's a good question. How we will sell it? I just got the idea, so I'm not selling it yet. But if we go back to the PLC part. The actual PLC programming language is actually pretty safe. Just remove it, if you. So it's yours. The actual PLC language is actually a safe language. You can do all kinds of things, and we can wire it to like some Erlang supervisors that restarts them. So that's kind of research I want to do next year. How I can get more Erlang features to the language, to the actual PLC developers. But for example, the predecessor of this hardware, which were two distributed RFID nodes, which were reading RFID Cyclic, is running for 1 year on the table of the engineer at the customer without interruption. And it actually talks to a PLC like you can buy in the shop. And the PLC needed to be restarted like 5 times in this time because it's actually written in C. And this is reliable. So I think there's a selling point there because we are more the slapped up prototype is already more reliable than a PLC than you can buy. So and basically selling this with the hard real-time stuff, I will use this to implement the PLC language where they can't break out, and actually they are not very depressed. They are actually very stressed. They have lots of work, the PLC programmers. So if you're like out unemployed or something like learn the PLC languages, it's very easy to get employment with this.
Okay, so let's thank Per again, and if you have any more questions, you can
yeah, talk to me.